We want to look at take-home problem 5. A pile contains 2 red balls and 3 blue balls. 2 balls are drawn one after the other and without replacement. Let X be the number of blue balls. Construct a probability distribution for X. Here we have 2 blue balls. You can't have up to 3 because there are only 2 balls, so you cannot have 3 blue balls. So you have only 2 blue balls, so the number of blue balls you can get are 0, 1, or 2. So the probability of getting, these are the possible situations. So here we have first blue, second blue, first blue, second red, first red, second blue, first red, second blue. So the probability of having no blue balls is both are red. For both to be red, that will mean that the first is red and there is no replacement, and the second is red. So there are 2 red and 3 blue. So here we'll have 3 over 5 and here 2 over 5. Here we will have 2 over 4 and here 1 over 2 because this is 1 over 2. Here we will have 3 over 4 and 1 over 2. So this is what we are interested on. Both are red. First red, second red is 2 over 5 times 1 over 4, which is 2 over 20. So 0 blue means first red and second red. First red is 2 over 5. There are 2 reds out of 5 balls. Second red is 1 over 4 because there is no replacement. So that gives the 1 over 10 for the first, for x equals to 0. For x equals to 1, you have either first blue and second red, or first red and second blue. So here will be 3 over 10. First red, second blue, 3 over 10. Here, this is first blue, second red. First blue, second red. First red, second blue is again, this is 6 over 20, which is 3 over 10. So we will get 3 over 10 plus 3 over 10, that gives us 6 over 10. If you don't understand, you can ask. So we have 2 cases. The first case is when the first ball is blue and the second is red. These are cases with exactly 1 blue. Exactly 1 blue is blue-red or red-blue. For blue-red, first blue is 3 over 5. Given first blue, second red is 1 over 2. If the first is blue, the probability that the second is red is 1 over 2. So we do 3 over 5 times 1 over 2. So this probability is 3 over 10. Second possibility is first red, second blue. First red is 2 over 5. Second blue, because there is no replacement, is 3 over 4. So we'll have 2 over 5 times 3 over 4, which is 6 over 20, the same as 3 over 10. So first blue, second red, 3/10. First red, second blue, 3/10. So this gives us 6/10. For exactly one blue. Yes. Because you are only choosing 2 balls. Mm-hmm. If you pick 2 balls, can they all be blue? Can you have 3 blue out of 2 balls? So we are only choosing 2 balls. Do we get this? We are choosing 2 balls, and we are counting out of those 2 balls the number of blue. We can only have 0, 1, or 2. Even though there are 3 balls, but we only choose 2 balls. The example I gave you in class, we wanted red, and there were 2 red. Yeah. But it wasn't 2 just because there were only 2 red, because we only choose 2 balls. Is it okay so far? If you have a question, please ask. Yes. Yeah, 3 said either this or this. So that's why we add, because it is either this one or it is this one. So there are 2 ways. Any other question for that one? Now for 2 blue, we have this one, 2 blue. It's 3/5 times 1/2, which is 3/10. When you finish, to be sure that you have not made a mistake, I mean, if you add the probability, you should get 1. Or the numerator should be added to get 10. If you get 10/10, that's fine. You can still get 10/10 when you are doing something wrong. But if you don't get 10/10, then definitely you are doing something wrong. If the sum of the probability is not 1, you are doing something wrong. If it is 1, it doesn't mean you are not doing something wrong. Okay? Sometimes things are like that. It will go one way, but not the reverse. So having this, we can find the mean. The mean of x is taking each value and multiply by the probability. So here, we have 0 times 1/10, 1 times 6/10, 2 times 3/10, and then we get 1/2. 1.2, I'm sorry. 6/5 equals to 1.2. To find the mean. To find the variant, you square each of the values of x. 0 squared times 1/10 is 0. 1 squared times 6/10 is 6/10. 2 squared is 4 times 3/10 is 12/10. So we have 6 plus 12/10, which is 18/10. The variance is the difference between the expectation of the square and the square of the expectation. So if you get your number of variance negative, probably you switch. It's always positive. If it is negative, then you did something wrong. If it is positive, you cannot tell whether you did something wrong or not. But if your variance is negative, you did something wrong. So we will get E of x squared is 1.8 minus 1.2 square, we get 0.36. And the square root of the variance is 0.6. Any question from the first question, the first exercise, number 1? Now let's look at this problem. An insurance company insures a person's antique car collection worth $20,000 for an annual premium of $250. If the company figures out that the probability for the collection being stolen is 0.02, what is the company's expected profit? You have more than one way to do this. I choose the one that I explained to you using the linear relation. That is, profit is equal to revenue minus cost. The revenue is the amount of money you get. How much money do the insurance company get? That is what is the revenue. How much they spend eventually is the cost. So here, the cost is very variable. Their cost will depend on whether the item is stolen or not. So the random variable here is the cost. If it is stolen, it will cost them $20,000. And the probability that it is stolen is 0.02. If it is not stolen, they will not spend any money. We assume that is 0, with a probability of 0.998. So using this method, we will have that the expected cost is 20,000 times 0.002 plus 0 times 0.998, which is 40. Then you subtract it from the revenue. You subtract it from the revenue. Here the revenue is constant. You pay the premium once. It's a fixed amount. So the money that the insurance gets for you is a premium that you pay a fixed amount, $250. So the expected profit to the company is 210. You could also make it as a profit random variable. To make it as a profit random variable, you will think about the two scenarios. If the item is stolen, the company gets $250, but spend $20,000. So you will do 250 minus 20,000, which is the cost. If the item is not stolen, the company makes $250 and you put. You can use this method too, and you will get the same answer. Question for this one? Yes. 1 minus this, the probability that it is not stolen. Complementary. Any other question? We can move to the next exercise. Here we are dealing with linear combinations and linear transformations. So let x and y be two random variables whose The mean of x is 130 and the standard deviation of x is 6. The mean of y is 120 and the standard deviation of y is 5. Let L be 2x minus 200 and W be 3x minus 2y. Find the mean, variance, and standard deviation of L. So for the mean E of L, we use the linear transformation formula for expectation. E of L is E of 2x minus 200, which is 2E of x minus 200, and which is 60. 260 minus 200. The variance of L is the square of the coefficient of x, the number in front of x, that is 2 square times variance of x, which is 4 times 6 square, which is 4 times 36, equals to 144. So the standard deviation is 12. Now, if we take the linear combination in where we combine two random variables, W is 3x minus 2y. Using the linear property of expectation, we have E of W equals to 3E of x minus 2E of y, which is 3 times 130 minus 2 times 120, which is 390 minus 240 equals to 150. If you have a question, just stop me and I will explain. Because this is how your exam is going to be. Yes. For variance, when you are dealing with variance, the constants always go. So the variance constant doesn't mean it doesn't change, right? So the variance of a constant is 0. The variance of W is the square of the coefficients times the variance of the variable, and we add them up. So we will have 3 square variance of x plus minus 2 square times variance of y, which is 9 times variance of x plus 4 variance of y equals to 9 times 6 square plus 4 times 5 square, which is 324 plus 100 equals to 424. And the standard deviation is square root of 424, which is 20.6. These answers, I think, are on Canvas. Is it not? Has anyone seen it on Canvas? Maybe I have not yet put it there. Let me just quickly check. I meant to put it on Canvas. Okay, it's not here.
Sorry for this. I want to put it here because I can plan to do it later and I forget. Okay, it is here. So the last question. The US Department of Health and Human Services reports that 7% of Americans has chronic sinusitis. If 5 people are selected at random, find the probability that exactly 3 will have chronic sinusitis. So you can use your calculator. You can use Google Scientific Binomial Distribution Calculator. You can use the table at the back of your book. But the table at the back of your book are limited to some nice probability like 0.1, 0.05, 0.15, 0.2, 0.25, 0.3. So if you have a probability like 0.67, you can use that one at the back of it. But with your calculator, you go to distribution, second function distribution, binomial distribution, or you just Google scientific calculator, no, binomial distribution calculator, and you will get a calculator that can give you answers to many of these problems. Let's do that one. But some of you are still writing. Okay, then we can use calculator. So to use calculator, you have probability of success is 0.07. Number of trials is 5. Binomial PDF. Second function, binomial PDF. So you will enter N, T, X. Binomial PDF, N, T, X. This is the probability that capital X is equal to small x, which is 3 here. So what do you get? Can somebody tell us? Somebody using calculator. 0.003. Next question is, find the probability that at least 3 will have chronic sinusitis. At least 3. The probability for at least 3, you can do either 3, 4, 5 or 0, 1, 2. It's essentially the same, but if you are using a calculator, it's better to do cumulative distribution for 2. And you will do probability that x is greater than or equal to 3 is 1 minus probability that x is less than or equal to 3. But the scientific calculator works better. Scientific calculator. I like this no, not scientific calculator, binomial. Binomial distribution calculator. So the probability of success here is 0.07. The number of trials, 5. Number of success, 3. So the probability that x equals to 2, do x equals to 3, will be 0.00296, which we round up to 0.003. The probability that for at least 3 is this last one. X is greater than or equals to 3. That's at least 3. So if it is the probability of less than 3, we are here, and this is what you will use for less than 3. Less than 3 means less than or equals to 2. Because it's either 0, 1, 2, 3. So if it is less than 3, it's either 0, 1, or 2. So this calculator, you get it from Google. But you can use your calculator because you can always have it. Now, what is the mean, variance, and standard deviation? For a binomial distribution, the mean is NP, which is 5 times 0.07, 0.35. The variance is NPQ, which is 5 times 0.07 times 0.93, which is 0.93. This is 0.35 times. Any questions so far? So this is take-home problem 5. We are going to go over take-home problem 6 on Tuesday. So as I said, submit it by midnight on Monday. There's a lot of time. If you have a question, you can always send me an email. I will help you. If it's during office hour, we can have a Zoom and discuss answers. Your exams will have questions that are similar to these ones. If you are able to do these ones, then you will be able to, it will be good for your next exam. We have, that exam will be next Thursday. It will be on chapter 4, 5, and 6. So make sure you go back to take-home problems, that you understand each of those problems. I will select some of them to make up the 5 exercises for the exam. Chapter 7. Yes. Yeah. Let me fix that. I did not publish this the week where it was supposed to be. At the beginning of this class, we learned that statistics consisted of collecting, organizing, summarizing, and presenting data using graph, analyzing to make conclusions or predictions about the population. The second part of statistics consisting of analyzing data to draw conclusions, make predictions, or generalize information is called inferential statistics. And in order to do this inferential statistics, we have learned some elements of probability that will help us in measuring level of uncertainty involved in our generalization. Suppose we did not know that if you toss a coin, you will get 50% chance of head or tail. Or let me put it this way. Suppose you are given a coin from a foreign country and you want to check if that coin was well made. So you want to decide what is well made, right? What do you think? What do you mean by the coin is well made? For you, the coin is well made will mean that there is an even number of ways to get head or tail from that coin. That is what is behind science. When I say this coin is not fair, it is only from the fact that I believe a fair coin should have a 50-50 chance of head or tail. Are you getting me? My fairness might not refer to color. My fairness may not refer to the value of the coin. You know, you can have a, let's say, a dollar coin, and the value of that coin becomes more than $1. Do you understand what I'm saying here? The material which is used to make that coin is now worth more than the coin. Do you know that? It is possible. You know what is used to make coin? You don't know, right? We don't know what is used to make coin. But the material that should be used to make coin should be equivalent to the value of the coin. Do you agree with me? Otherwise, that happens in some countries where the government spends so much money to make good coin. That coin is supposed to represent the value of money. But yet, the material used to make the coin has more value than the coin. The population are unaware of that. Some people come and buy those coins and go and melt it to make jewelries. You see what I'm trying to say here? I am diverting a little bit for what I was trying to say. But the reason I'm saying this is because when we say fair, it's fair with respect to an understanding of ourselves. Do you get what I'm doing? So whenever I call fair coin, it means 50-50 chance of getting head. We agree on that. And I gave this example to tell you that that might not be all about being fair. But for me, that is what it is. And when I get on TV and say, this is not a fair coin, people might just begin to think. Everybody will draw his own understanding of fair coin. He might be saying it is not fair because the value of the coin is more than the actual face value. He might be saying it is not, everybody will go with whatever, and those are some limitations of science. Now, coming back to statistics. If you find a coin somewhere, an antique coin or something like that, and you want to check if it is fair, you might decide to toss it maybe 2 times. If you toss that coin 2 times, and both times you get head, we do infer that that coin is not fair. You will feel free to ask. We are just discussing. We do infer that the coin is not fair. If you toss it 2 times, and then both times you get head, will you just feel like, no, this is not a fair coin? You don't feel like judging? You know, people like judging a lot. But when it is judging for brain, they run away. Okay, so we will feel like 2 times is not enough, right? And we will say, let me try 3 times. If the third time you still get back, you will begin to question. So what we are going to learn in this chapter is, when do we start beginning to question? At what point do we raise suspicion? We are going to learn that in inferential statistics. We are going to be discussing sample size. In chapter 6 already, we say that if we don't know the nature of a distribution, then the distribution of sample mean will be approximately normal if the sample size is large enough. And we felt like large enough to us is at least 30. So from 30, we will begin to feel like the shape of the sample mean distribution will begin to be like a bell. So now, if you toss your coin 20 times and you get 9 heads, will you conclude that this is not a fair coin? You may not conclude, right? Because 9 is kind of close to 10. So in this chapter, we are going to learn to find the range of values within which we expect our parameter to be. We can say that a coin is fair if the number of heads is between 9 and 11. Could be 9, 10, or 11. Or we could draw back a little bit and say, anyway, 8 could be acceptable. Okay, 8, 9, 10, 11, 12. So the actual parameter is 10 out of 20, which is hard, right? If you toss 20 times. So we know we are not sure we can always get half. But how far away can we depart from it is our question. The difference between the statistic you get when you do the actual experiment and the actual parameter is called an error, a sampling error. So we are going to learn about the maximum error of estimates. So first thing we want to think about is the connection between a statistic and a parameter. So a statistic will be called here an estimator of a parameter. A statistic is an estimator of a parameter. And we will say that an estimator is considered good if it is not biased. What we mean by it is not biased is that the expected value of that estimator is the parameter. That means when you use that statistic, which we are calling estimator, you expect to get the parameter. For example, we consider the sample mean as an estimator of the population mean. We check, is it a good estimator? What is the expectation of the sample mean? If you remember what we did in 6.4, we said the expectation of this was what? The population mean. So that means the sample mean is a good estimator, is an unbiased estimator of the population. So we want a good estimator to be consistent. Consistent will mean the larger the sample size, the closer that estimator should go to the parameter. For example, if we take proportion, if we want to know the proportion of students who like wearing masks, for example. So we will take a sample of 20 students and ask them the question. But if we take a sample of 50 students, do you think we will get a better estimate of the actual parameter if we increase the sample size? I think so. What about you? The more people you interview, the better your estimation is. Those are the issues with some of those polls for some of you who are interested in politics. When somebody gives you a poll, if you want to determine how reliable is that poll, we are going to talk about reliability. You want to look at least at the sample size. How many people? Out of 300 million people, if somebody sampled 1,000, is it really something I can rely on? Those are a lot of aspects of things that are not being told on TV. So it is unbiased, it is consistent, and it is relatively efficient. That is, it is reliable. Reliable means it does not change a lot. That means the standard deviation is the smallest of all the other estimators. Remember the standard deviation for the sample mean is sigma over square root. If you take a variable, an estimator or a statistic like the mode, you can increase the sample size and the mode change to something else. Do we understand what I'm saying here? The median, you can increase the sample size and the median remain the same, especially if you have the same number at the bottom and the same number at the top. You are not going to be changing the median. If it wasn't the actual parameter, it is not still going to be because you are adding. So those are not very good estimators. So the sample mean is an example of a good estimate. The sample standard, the sample variance is also a good estimator, but for the population variance. The sample variance is a good estimator of the population variance. But the sample standard deviation is not a good estimator of the population standard deviation. So we mathematicians, we are interested on the number. So if we can estimate the variance, we can still use the standard deviation, but not relying on the theory of estimation, but relying on the fact that standard deviation and variance are kind of connected. So these are just some introduction before we get into the mathematics. So some of these things, I say it and just for completion. The margin of error, as I told you, is the maximum error of estimate. Suppose somebody wants to tell you the proportion of students who like wearing masks, so that you take your decision whether you should go to that school or not. And then he says the proportion is 40%. How did you get the 40%? I took 10 students and then 40 said they like wearing masks. 4 said they like wearing masks. You might feel that, I'm not so sure that I want to trust that, because your sample size was small. How wrong will that be compared to the actual value? You cannot tell me. So the maximum error of estimate, which we will call E, is generally determined using a confidence level, using probability. And it is used to determine how far we can go wrong while being acceptable. For example, I can say, I want you to toss a coin 50 times and tell me the proportion of head. Or I can want to think, we are going to answer that question, do that kind of problem also in this chapter. If I want to be 99% confident that the result you are getting is not too wrong, is wrong but not too wrong, by maybe more than 0.1 or maybe more than 0.01, then how many people should you get? Anyway, so I know this theoretical part looks. So the confidence level now is what? The confidence level, we have two types of estimation. You can estimate using a point. We call it the point estimate. You use a point. It is called a point estimate, mean you are using a specific number, like the sample mean is a point estimate. You can use an interval estimate, meaning you are using a range of values. For example, I can say the average age of St. Francis University students is between 17 and 23. That is a range. We call that an interval estimate. But if I take a sample of 50 students and find the average age to be 19, I will say that the average age of students is about 19. That is a point estimate. So we use the point estimate to get an interval estimate. And we want to realize that an interval estimate gives us more information than a point estimate. Either the point estimate is true or it is not. But an interval estimate will give us a range of possible values for that. So when we are talking about confidence level, we are looking at interval level, a range estimate based on sample size of the same size, and what proportion of those intervals will actually contain the parameter. So when I say that the average age is between 18 and 22, is it true or not? So it might be true, it might be false. But you might use several samples. Each of us can take a sample of 50 students. I use our sample mean to estimate an interval range of the age of students. Then some of us will actually get an interval that contains the parameter, some will not. The proportion of intervals that will contain the parameter is called the confidence level. It will generally be given to you. So now let's look at confidence level and margin of error. So if you want to write something, X bar is a point estimate for mu, the population mean. If the population is normally distributed, or the sample size is large enough from the central limit theorem, then the distribution of sample mean will be bell-shaped, approximately normal. The sample mean here will have a mean mu, the population mean. You can say mu, the population mean. So we can decide using the confidence level, for example, of 90%. If the confidence level is 90%, that will mean that we want to find a possible range of values so that 95% of interval estimate will actually contain the mean. So E is here, is called the margin of error. So if we reduce this to 0, that is by standardizing it, then we will have two numbers here, Z alpha over 2, Z alpha over 2. So alpha here is 1 minus the confidence level. If the confidence level is 90%, alpha will be 10%. So here we will have 45% and 45% here. And this tail will be alpha over 2. So based on this confidence level, the distance from here to here is minus Z alpha over 2. And if you could remember when we were learning about the normal distribution, we call this Z the number of standard deviation we are away from the mean. So we will say that E is equal to Z alpha over 2 times the standard deviation of the mean, which is Z alpha over 2 times sigma over square root of n. This is the standard deviation for the sample mean. So when we have the margin of error, where do we get this Z alpha over 2? You can use your calculator to get it. You have done it already. In your textbook, you have a set of tables that have the Z alpha over 2. On this PowerPoint, you have it. These are the possible Z alpha over 2 for the given confidence level. So I usually give 3 that comes too often. Your book writes this ZC, C for critical. We are going to learn that later. But I like writing Z alpha over 2 because it's the Z value so that the area to the left of Z is alpha over 2. So if you take 90%, it will be 1.645. If you take 95%, it will be 1.96. And if you take 99%, it will be 2.58. If you want to check that with your calculator, just take for 90%, alpha over 2 is 0.05. The procedure is subtract the confidence level from 1, divided by 2, and get into distribution, inverse normal, area 0.05, and you will get negative 1.645. So Z is 1.645, minus Z is negative 1.64. If you forget that, you can use your calculator. But yes, you go to second function, distribution, and then you go down, maybe the third one, inverse normal. Yes, third one, inverse normal. And then just enter 0.05. And what do you get? Negative 1.645. If it was 0.95, you are going to enter 0.025. It's 5% divided by 2, 2.5%. 2.5% is 0.025. If it is 99%, you have 0.01 divided by 2. It will be 0.005. Whatever it is now, if it is 85%, the tail will be 0.15 divided by 2.075. If it is 98%, the tail will be 0.02 divided by 2.01, and you enter into your calculator. So you can get this Z alpha over 2. This table is available for you on your PowerPoint. It is at the back of your book. No, on the formula sheet that is in your book, you have this. You will need it sometimes, but not. Okay. So at this point, we want to say that we can compute the confidence interval for the mean if we know the confidence level and the standard deviation of the population. So we are going to discuss two cases. The first case is if sigma is none. We are going to discuss two cases where we are
confidence interval you can say if sigma is known, use the Z distribution. The margin of error is E equals to Z alpha over 2 sigma. If sigma is unknown, we are going to discuss this more on Tuesday. Not that we are done, but I will leave this second part, but I just want to mention it now so that you see how connected we are. If sigma is unknown, we will discuss the T distribution on Tuesday. We'll still have more to do here. Use the T distribution, and E will be T alpha over 2 S over square root of n with degree of freedom n minus 1. So the reason why I'm putting the two cases is because the confidence interval is x bar minus E less than or equal to E less than or equal to x. So each of these is done based on the fact that the population is normally distributed or the sample size is large enough. Otherwise, we cannot do any of the two. To use the Z distribution, which is what is easily accessible commonly, you want to have sigma. If you don't have sigma, you will use the T distribution. So in your take-home problem, generally I will ask you, which distribution should we use? The most important element there is availability of sigma, the population standard deviation. But other conditions about it are populations are normally distributed or sample size is large enough. They are both necessary for each of the two situations. Let's do an example here. We can also use calculator. Do you like learning how to do it manually or using calculator? Should we learn both? Or learn how to use calculator only? Somebody prefer calculator? Calculator. Okay, calculator is winning. Somebody prefer manually doing the mathematics? Why do people hate mathematics? They hate it and they don't like saying it. Okay, I'm going to be doing both, but focus on calculator. What about that? I'll show you how to use calculator. You focus on calculator because I'm not going to ask you to use manually. I'm just asking you to do something. If you want to do it manually, but there's room for mistake manually. I'll use calculator. So let's do this. We will do both for this. Julia enjoys jogging. She has been jogging over a period of several years, during which time her physical condition has remained constantly good. That's what happens when you do sports. Usually she jogs 2 miles per day. The standard deviation of her time is sigma equals to 1.8. How did they know this? Probably from past experience. It is usually an estimation. But we want to use it for our example, because if we don't know the mean, how do we get the standard deviation? So the reason I'm saying it is because most of the time in problems, you will hear that from past experience, the standard deviation was known to be that. During the past year, Julia has recorded her time to run 2 miles. She has a random sample of 90 of these times. For these 90 times, the mean was 15.60 miles.
So what is her sample size here? Anybody getting what we are doing? What is her sample size? Yes. Our sample size is 90. So we will record n equals to 90. What is her sample mean? 15.6. And what is the standard deviation of her running time? You see, this is for the sample, but this is her running time in general. Okay? We don't usually have this easily because how will we get it? But sometimes we use past research to get sigma. So we are assuming in this class that we know sigma. So our question is, what is the actual average running time for 2 miles, which we don't know? Let mu be the mean jogging time for the entire distribution of Julia's 2 miles running time taken over the past year. Find a 95% confidence interval for mu. So C equals to 0.95. Our next question is, what distribution are we going to use? So here we want to realize that because our sample size is large enough, we can assume that the population, the distribution of sample mean is approximately normal. We can assume that. Because sigma is known, we can use the Z distribution, the Z interval. So on your calculator, you will go to start, then test, then choose Z interval. You choose Z interval because sigma, the population standard deviation, is none. Can we use calculator? Try using your calculator. That's what I'm waiting for you to use calculator. Then after you use calculator, I will do it manually. So you go to start, you will see start on your calculator. Then if there were data, you will go to edit. We are going to learn that next time. But for now, you go to start, then test. Then among the tests, you scroll down, you will see Z-test, T-test, forget about those. We are looking for Z interval. Do you see Z interval? Thank you. Number 7, Z interval. Then you have the choice between statistic and data. Data is when you have a lot of values. Statistic is when you have just the main information. So you choose statistics. When you choose the Z interval, it will start with standard deviation of the population, sigma. So what is sigma? So now if you have a question, you can ask me because it will ask you for information. If there is something that it is asking that you don't see, please ask me. Confidence level 0.95. Sample mean 15.6. When you are done, you click maybe calculate or something. Yes. This is not mine. Somebody forgot. Anybody has something for the confidence interval? You will have a parenthesis with two numbers. What is the lower number? Nobody is having something? Is it 15? Okay, can we write like this? Anybody has this number? Okay, why were you not saying something before? And the upper one? Is that what you are getting? I don't know because I don't have it, right? So if all of us are getting it, then it is right. What about that? Okay, then I just show the PowerPoint. So now for C equals to 0.95, Z alpha over 2 equals to 1.96. Then E equals to 1 Z alpha over 2 times sigma over square root of n, which is 1.96 times 1.80 divided by square root of 90. We will get 0.37. 0.37. We get 0.37 as E. Add it to this. You get that. Subtract it, and you get this. If you can see, 0.6 plus 0.37 give you 0.9. Yes. When C equals to 0.95, Z alpha over 2 equals to 1.96. To get it, go to your calculator, second function, distribution, inverse normal, 0.025. Or you just come and look at it here. I have this table like 2 or 3 times in this PowerPoint. So we are going to learn how to use calculator to get it, but you need to know what tests are we using. What is sigma? What is S to put into the calculator to get the confidence level? Okay. So you can go over the PowerPoint again. We will continue on Tuesday.